This is Science Max, experiments at large. Science Max!
This is a string. You can pull a string, but you can't push a string. Well, you can. You can push a string. You really can. Okay, quit it. Quit it. This little contraption works sort of like a baseball pitching machine, but in miniature. See, there are two motors here, and the wheels spin together to shoot things out this way. Things like this craft stick. Watch this. Whoa! Let's watch that again. Whoa! But now, watch as I put a large loop of string through. What? Pushing string. How does this happen? Hello?
I don't suppose it's the Magnus effect?
No, it's not the Magnus effect.
No, it's all right. I'll be in my lair if you need me.
Okay, right. Bye. Right, where was I?
I believe you were at, the reason why this works is...
Right, pushing string. How does this happen? It's all because of inertia. Check it out. The wheels are pushing the string through fast. It's got some weight and it's got some speed, which means it has some inertia. So when it goes this way, it wants to keep going this way. But it goes all the way to the end, and then because it's a loop, gets sucked back in this way, which means all of this inertia, you can sort of overcome gravity. Pushing string, science. Now it's time for one of my favorite scientific terms, the Magnus effect.
I am Magnus, and behold my effect.
No, the Magnus effect has to do with things that are spinning. Things like these cups. And here's a great little Magnus effect flyer you can make at home. It's super easy. Get 2 styrofoam cups and tape them together at the bottoms using science tape. Then get some elastic bands and make a long one by tying them together. Take your elastic and you wrap it around the cup like this. Then hold the elastic on the bottom, remember, like that. And then let them go. They fly up and out. The reason why it goes up and stays in the air is because it's spinning, creating moving air over the top. Moving air has lower pressure, which means it's pushed up by the higher pressure underneath. And that is called the...
It's coming.
Oh, come on.
Oh. Now, the Magnus effect.
Yes. So, let's max it out.
Magnus it out. See how much better that sounds?
No. Max it out. Check it out. Magnus Flyer 2.0 stand elastic slingshot. Wrap it around. Remember, for the Magnus effect to work, your cups need to be spinning this way, the front side rotating up.
Oh, and there you have it, the Magnus effect. I, Magnus, am out taking over the show. It is now Science Magnus. That is my effect, slightly improving the name of science TV shows. Science Magnus.
This is hydrophobic coating. Hydrophobic literally means afraid of water, but it's not actually afraid of water. The chemistry of a hydrophobic coating prevents water molecules from penetrating anything you spray it on. You can get this stuff at the hardware store, and if you want, be Science Maximites and get an adult and think of the coolest thing you could spray with hydrophobic coating. I like to use things that do not go well when you put them in water, like tissue. Yeah, doesn't look great when it gets wet. Here's a tissue coated in hydrophobic coating. Huh? Weird. Or it works the same with a paper towel. Paper towel in water, paper towel covered in hydrophobic coating, stays dry. Or how about a dinner roll? Dinner rolls really don't like water. See? Gross. But a dinner roll coated in hydrophobic coating? Weird. Just don't eat it. Now, it's time to max it out. I have coated half of my lab coat in hydrophobic coating, and the other half I have not. Hydrophobic coating, regular lab coat. Half of me is wet and half of me is dry. What's more, half of my outfit ended up being wet and half dry because the lab coat was protecting my outfit from getting wet. Now it's time to max it out even more. We have coated my entire outfit in hydrophobic spray. My shirt, my pants, and my lab coat. The pants have been taped to rubber boots, so no water's getting in there. And my shirt has been taped to my pants, so no water's getting in there. So here's the question. Can I get into the pool and out of the pool and stay dry? Let's find out. In the pool, out of the pool, and I'm still mostly dry. Now here's what really happened. I got into the pool and I realized I should have duct taped the pocket because all the water went in there, down into the rubber boots, started filling up the rubber boots, and now my entire leg is full of water because the hydrophobic coating isn't letting it come out. So the hydrophobic coating isn't keeping the water out, now it's keeping the water in.
Let's take a closer look at Newton's third law.
Newton's third law. For every action, there is an equal and opposite reaction.
Okay. All right, let's watch it back.
When the sign hits me, I exert a force on the sign in the opposite direction. That makes the sign stop moving. It also exerts an equal force on me, causing me to fly off in this direction.
Now, if I was to push this sign, I'm not only pushing the sign this way, but my feet are pushing against the ground in the opposite direction. It's, well, it's really easier to see if I'm not standing on the ground. No, hold on. Okay, so, okay. So now that I'm hanging, watch. I push on the sign, but when I exert force on the sign to make it go this way, I go that way. Well, actually, it doesn't work as well because the sign isn't as heavy as I am. So wait, I have this over here. This is a barrel, and it has stuff in it, and it weighs as much as I do. Okay, so watch. If I push on the barrel like that, I go away from it as much as it goes away from me. So, there you have it. Newton's
third...
No, hold on. Newton's
third law.
Newton's third law. Okay, go.
Newton's third law. For every action, there is an equal and opposite reaction.
This science is delicious. This is rock candy. It's basically crystallized sugar, and you make it by turning a solid into a liquid and then back to a solid again. Here's how you can make it at home. You need a container that you're not gonna need for a while, and some water, some sugar. You can use brown or white. I like to use brown. And an adult. Here's why you need an adult. You want to dissolve 3 cups of sugar into every cup of water, and you can't do that unless you heat the water. So get an adult, a saucepan, and heat the water up, pour the sugar in, and keep stirring until it's all dissolved. Then pour it in your container and let it cool down. Then you'll need a shish kebab skewer, which is something you can get at the grocery store. Cut it down to the right size so it fits nicely into your container, and then dunk it in your sugar and get some crystals coated around the stick. These are seed crystals, and they get the whole process started. And now you have to wait for these to dry, otherwise they'll just fall off the stick when you put it in the water. So I've got one here that has dried out. You'll also want something to keep it from falling in the top of the container, so I'm gonna use a clothespin. Put it in there and dunk it in the container like that. And now for the final step, if you want, you can add food coloring. I like to use red because it reminds me of science. And I'm gonna use the stick to actually stir that up a little bit. There we go. Now, the dissolved sugar crystals in the water will slowly grow on the crystals that are already attached to the stick, and it will eventually grow into a rock candy pop. But it takes about a week. No, I'm just kidding. I've already got one that's standing by. Here we go. This one has been growing for about 7 days. And there you go, rock candy. delicious science. Now, how can we make this any better? I mean, it's crystallized sugar. It doesn't get any more maxed out than that, does it? Yeah, it does. Come on. This is a giant container of sugar water, and I've been brewing a massive rock candy crystal in it for a while, but it's sort of getting a little bit too big to fit out the top of the container, so you know what? I'm just gonna put that back in there and chalk that one up to science because, well, eating a rock candy crystal that big would definitely not be good for my teeth, so yeah.
Being a chef is my absolute passion, and cooking up science recipes is my speciality. I'm Buster Beaker, and this is Cooking with Science.
Oh, hello! Welcome to Cooking with Science. I'm Buster Beaker. Whenever friends come over, I like to make my famous potato chip recipe. And look at this bag of potato chips. Quite large, there must be a lot of potato chips in here, right? Well, let's open it. What? This potato chip bag is mostly air. Why do potato chip bags have so much air? Well, to tell you the answer to that, I have to tell you the story of 2 bags of potato chips. Here they are. This one full of air, and this bag of potato chips, there's not much air in it at all. Why don't they make them like this? Well, let's find out. First thing that happens is the potato chip bags come off the conveyor belt at the potato chip factory where they get packed into a crate. Here's a crate here. So let's really stuff them in. And then the crate gets boxed up and shipped off to the store. Oh, it's a bumpy ride to the store today. Now we're at the store, and then you come along. Bags of potato chips. What else should I buy today? Oh, I know. How about a cantaloupe? Very nice. Some apples, yes? And take it home, walk along, and you get to the kitchen, you have a choice. This bag of potato chips, where all the potato chips are light and fluffy, or this bag of potato chips, which is not exciting at all. And that's why potato chip bags have so much air, to protect the potato chips from getting crushed. Speaking of potato chips, time to get back to my recipe. What is it? It's potato chip soup. Well, I'm Buster Beaker, and thanks for joining me on Cooking with Science. Perhaps a little bit more cooking.
Oops. An egg. Now, you might think of eggs as kind of flimsy, and they do break pretty easily, but eggs are actually stronger than you think. It's because they're, well, egg-shaped. You see, the top of the egg is like a little bit of an arch, and the bottom of the egg is also like an arch. And arches distribute the weight, just like they do in a bridge. Here's how you can experiment with how strong eggs are. First, you want to get a pair of gloves to protect your hands from the shell, just in case anything goes wrong. You should also tell an adult that you're doing this experiment because if it does go wrong, you're gonna have some mess to explain. And also, you should probably put on some safety glasses. Now, here's what you do. Take your egg and carefully put it in your palm just like that. And put it against your other palm, and you're gonna push in directly on either side of the egg. Start pushing harder and harder. You can even lace your fingers and press even harder. And if you do it right, the egg won't break. Pretty amazing, right? So, just how much weight does an egg hold? Can one egg support my entire weight? Let's find out. I'm gonna lift my weight up like this and lower myself down. And no, cannot hold my weight. Can my weight be supported by 2 eggs? Oh, nope. Phil's weight, 4 eggs. Oh, I thought they were gonna do it. Nope. My weight on 8 eggs. My weight can be supported by just 8 eggs. Science! Whoa, careful. Chris and I are maxing out a hydraulic crushing machine. What about this? Is this what we're gonna use? We went to the Natural Resource Canada's CanMet Materials Laboratory, which is a federal research lab. Oh, this is good. Oh, look at that! Oh, is this what we're using?
No, Phil,
oh, I
it's
can
actually-
use this. Hold on, let me figure this out.
Maybe later.
Really?
It's just over here.
CMAT is the largest research center in Canada dedicated to metals and materials research.
This is it. This is
Yeah, right! Hydraulic press. How much force does this apply?
it. This can do 2 million pounds,
That's over 900,000 kilograms.
which is about 20 cars.
Let's crush some stuff! Oh, crushing! We gotta get the stuff. We started out with the piece of wood which defeated our last press. And go!
that sound.
Awesome. Reversing. It turned our wood into a pancake. Whoa, totally flattened. So it was time to try some other stuff. We crushed a ball of plasticine. That is neat. You sort of made a rainbow.
Yeah.
Aluminum foil.
Aluminum foil.
Yes, it is now a solid plate of aluminum.
And a basketball. Basketball. Good thing we got these earplugs in because when it pops, it'll be loud.
What?
Never mind. This hydraulic press was so maxed out, we had to think of the toughest stuff to crush. We crushed hockey pucks, a safe, we crushed a hydraulic jack with the hydraulic press. This is a metal vise, hard, strong,
Yeah, steel.
heavy, steel.
Whoa, look at it bend. Wow.
Now it's time to crush a bowling ball. It totally exploded. Science Max! Experiments at large, hydraulics. Whoa. Nicely done.
So fun.
I should reverse it and we should start cleaning all that stuff up,
Yeah,
huh?
I think so.
Okay, reverse.
Being a chef is my absolute passion, and cooking up science recipes is my specialty. I'm Buster Beaker, and this is Cooking with Science. Strange. The spoon is no sharper than it was before. Oh, hello. Welcome to Cooking with Science. I'm Buster Beaker, and today we're cooking with coal. Today we're going to learn how to make a drink cool. Look at this bottle of lemonade. It's warm right now and not very refreshing. So what's the best way to cool this down? We put it in ice, right? But did you know there's an even better recipe than ice? You can make ice colder. It's true. All you need to do is add salt. I've got a second bowl of ice and a second jug of lemonade, and I've got 2 digital thermometers. What I'm going to do is add salt to this bowl. What the salt does is starts to melt the ice, and that actually consumes heat. This is called an endothermic reaction, and it absorbs heat, which makes the ice colder. And as you can see, this bowl of ice still sitting at around 0 degrees Celsius, but this bowl, -8 and falling. Wow. So there you have it, making something even colder than ice would normally make it. That is a way to make a refreshing glass of lemonade. I'm Buster Beaker, and thank you for joining me on Cooking with Science.
Inertia. What is it? Well, it's directly related to Newton's first law of motion. An object in motion tends to stay in motion, an object at rest tends to stay at rest. Let's do an experiment. Here is an object. Right now, it's at rest. You might think that means it has no inertia, but that's not true. Inertia just means an object's tendency to keep doing what it is doing. Right now, it's doing nothing. But if I wanted to overcome its inertia, I would have to put energy in. And now that I have, it is moving on its own. It has inertia. If I wanted to stop it, I would have to overcome its inertia, its tendency to keep moving. There. I went exactly that far. Now, let's max it out. I'm adding these weights to the cart. Now it has a lot more mass, which means it has a lot more inertia and its tendency to do nothing. But this time it has a lot more inertia. If I wanted to get it going the same speed as before, I'd have to put in a lot more effort. There, now it's going the same speed as before, but now it has way more inertia, so stopping it will be harder. So there you go, inertia. A thing's tendency to stay moving or stay still, and the more mass, the more inertia. Dear Phil, I can't believe you did a whole episode on boat propulsion and you didn't use the greatest thing out there for making a boat move, a propeller. Sincerely, a fan. Well, let's talk about propellers. Oh. Good thing this is fan mail. Get it? Because it's a fan? Yeah, anyway. A fan pushes air just like a boat propeller pushes water. They're both fluids and they behave in the same way. Now, if you look closely at a fan, it's curved on the blades. The air or water is caught under at this side and then it's pushed out on the curve to make it go that way. And the faster it spins, the better it works. Now, this is a propeller-powered boat. And what you do is wind up the propeller. I have an elastic band here to store the amount of energy I put in. And then you put it in the water, the propeller spins, and the boat goes forwards. It's being propelled by the propeller. That's why you call it that. Awesome, right? Well, now we'll max it out. This is a drill. It spins. And this is a propeller, and when you put it in the water and spin it, it provides thrust. So let's try it out. Whoa! Remember not to try this at home. I am a trained professional. This is a very small propeller. Let's compare. This is a super maxed out propeller. Whoa, okay, let's try it out. Whoa! The larger a propeller is, the more energy you need to turn it, and the more propulsion you get out. Greetings, Science Maximites. My name is Phil, and welcome to Science Max Experiments at Large. At this very moment, half the lab is being held together with the power of electromagnets. Magnet 1 turning off. Electromagnets are a really cool and powerful way to interact with the world. And when I say power, that's because you need power to make them work or not work. Magnetism is an invisible force that has to do with the magnetic fields created by magnets that lets them attract things that are metal or each other. But electromagnetism is a little different. You see, magnets are magnets all the time. It's because of what they're made out of. Electromagnets are only a magnet when you have an electric current going through them, which means you can turn them on or off. Today, we're gonna be building an electromagnet. Oh, that was the wrong switch. Anyway, like I was saying, today we're gonna be building an electromagnet. You need a bunch of copper wire, a very large nail, or something metal to become your electromagnet, electrical tape, a battery, an on-off switch, wire strippers or a craft knife, and the help of an adult, and finally, something to magnetize, like these paper clips. And remember, all of the steps for this experiment are on the website. To begin, take the copper wire and start at the top of the nail. Leave a little bit of wire sticking out, then carefully start to wrap the wire around the nail. Don't go all the way to the end because you need some metal to turn into the magnet. Instead, when you want to start again, run the wire straight back to the top and start wrapping again in the same direction. And keep wrapping and wrapping until you get to this. Now, I've used some electrical tape here, here, and here to hold it all together. Using your wire strippers or a craft knife and the help of an adult, remove the plastic coating from the ends of the wires. Attach these wires to the wires from the on-off switch with electrical tape, or attach them directly to a battery if you don't have an on-off switch. And ta-da, you have an electromagnet with your on-off switch. All you need to do is take the things you're going to magnetize, turn your electromagnet on, and suddenly it becomes a magnet. Pretty amazing, ha 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 ha. And then you can magnetize to your heart's content. But when you're done, don't forget, you want to turn it off. So that's what we're gonna do today on Science Max, Experiments at Large. We're gonna max out the electromagnet. So, where's my lab coat? Oh, there it is. We're gonna see how big we can make an electromagnet. And when I say we, I mean me and an expert. Let's see. Oh, Heather from the Ontario Science Center. She knows her way around magnets. So let's see. Yeah. I wonder if she's busy. Well, let's find out. You may recognize this. It is a spring. Yes, good for you. But did you know that springs can defy gravity? Whoa!
Gravity-defying.
Look at it fly! Defying. Okay, not exactly, but what if I was to hold the spring like this and let it go? What'll happen? It'll fall. Yes, it'll fall. That is true. But while it's falling, what happens to this end? Does it stay in one place? Does it go up? Or does it go down? Let's find out. I'll bring this in so you can really see it. Okay, ready? Watch close. Did you see? Did you? No? Okay, tell you what. We'll watch it again, this time in slow motion. See? The bottom doesn't move, and here's why. When the top of the spring is released, gravity and the tension of the spring are pulling on it. The bottom of the spring is being pulled down by gravity and up by the tension of the spring. These forces cancel out, stopping the bottom of the spring from falling until the top reaches it. Until there's no more tension, and then the top passes the bottom and the whole thing. That is how it works. But here is the real question. Will it happen differently with a longer spring? Huh? Well, I just happen to have a longer spring! Let's max it out! Bring it. Don't tangle it. So, now that I'm up high on this fire escape, let's test it out. Okay, 3, 2, 1, go! A longer spring still has the same forces working on it. The tension of the spring pulling it up and gravity pulling it down. No matter what size of spring, these forces cancel out for the bottom of the spring until the top meets up with it. So there you go, an almost gravity-defying spring! Hey, there's no door handle on this door. I guess I have to take the stairs. Whoa. This is a basketball. It bounces. This is a golf ball. It bounces. but it never bounces as high as where I dropped it from. But watch as I put the golf ball on top of the basketball. Whoa! Why does the golf ball bounce higher than where I dropped it from? How is this possible? I only bounced the golf ball from 1 meter high. So what's going on? Well, as the basketball hits the ground, it compresses, storing the potential energy of its bounce, about to give that energy back as it bounces up again. But this energy works as a springboard for the golf ball. And since the golf ball has a lot less mass than the basketball, the upwards kinetic energy of the basketball is given to the golf ball. So, let's max it out. Ball, on a ball, on a ball. 3-ball bounce. Oh, did you see that? Ball, on a ball, on a ball, on a ball. Quadruple ball bounce. Oh, oh. Oh. No, wait. Turns out getting 4 balls to drop straight down on top of each other is pretty difficult. So, we know the mass of the ball is important. Why don't we max it out in a different way? This is a Swiss ball for exercising. It has a lot more mass than a golf ball. So, let's try it out. There you go. The transfer of energy between balls. A great way to lose golf balls. This is a bike tire. It's pretty light, but I still can't hold it from the end of the pole like this with one hand. Nope, nope. But I can if I get it spinning fast enough. I just use this drill, and then I get... Okay, so this is gonna be awfully hard to do with one person. Oh, this is the perfect opportunity to use the Trevor button. Haha, Trevor button. Hey, Trevor from the Science Max build team. What are you doing?
Maxing this out.
Oh, right on. Can you give me a hand for a second?
Sure.
Awesome. Okay, so you take this drill, and we're gonna get this wheel spinning really fast.
Okay. I don't know if it's,
No, I don't wanna know.
I don't know if I remember to...
No, it's fine. Max it out. We gotta max it out. So, because it's spinning, I can hold this heavy weight in the air. How is this possible? Because the wheel is basically a top. The forces that prevent a top tipping, angular momentum, are still working here. This angular momentum resists a change in direction, this way, which is how gravity would want it to tip. Interestingly, these same forces also keep it spinning around me in a circle. So, I can lift a heavy weight in the air just by spinning it. Awesome max out experiment, Trevor.
Yeah!
What was that?
It's my science confetti high five I just made.
You know what we should do?
What?
We should max it out. Yeah, we can make a giant one and then a whole bunch of confetti in it, and then people like jump up and do more confetti that would come out, right? And then so what would happen is there would be all this Trevor? As you may have already guessed, today is about friction, and here's a really easy friction experiment you can do at home. All you need is a piece of wood. You don't need the frame, and you don't have to do anything fancy to it. Just put one end up on a couch or a coffee table and make a nice ramp. Then you want something to slide down that ramp, and I like to use a piece of wood. Now check it out. Wood ramp, wood block. The friction is so much that the wood slides to there. Now what I like to do is take a little flag and mark the results. Recording the results is good science. Now here's where it gets fun. Get another surface and attach it to the wood, like carpet and wood. Let's see how far this goes. Not as good. All right, record the results. Cardboard. Ooh, nicely done, cardboard. Foam. And this wood has been waxed, like on a floor wax, which makes it nice and slippery. Let's see how that does. Ooh. And now the ultimate ice attached to wood. This is actually harder to do than I thought. All right, let's try it out. Ice! The clear winner. Not a big surprise right there. And get this, once you've done all of that, you can change the surface of the ramp. You can go to waxed wood, carpet, boom, cardboard. Well, well, yeah, you get the idea. Record all the results, compare them, and there you go. Friction ramp experiment. And that's what we're gonna be maxing out today. So come on, let's go. If you attach something ferromagnetic like this washer to a magnet, not only does it stick, but the magnetic field travels down the metal, making it a magnet too, which means you can stick more and more things to each other, and they will continue to stick until you run out of magnetic field. You can do this yourself at home with anything ferromagnetic. Paper clips work pretty well, or washers like I have, or screws or bolts, and they'll continue to stick to each other as long as the magnetic field is strong enough. You can see it's getting pretty weak here, and they'll all stay magnetized as long as the first one is still attached to the magnet. But if you want to go even further, all you need to do is keep adding more magnets to reinforce the magnetic field. I've got a few here, like this. Let's get the chain started, like that. And then I've got a magnet attached to this washer, so it will keep the magnetic field strong. And I continue to add one magnet, one washer, and we'll just see how far I can go. You can even sculpt it a little bit. Look at that. And then at the end, a whole bunch of paper clips. Eventually, the weight will make it fall off, but it's a lot of fun to play with magnets and make art. Speaking of art you can make with magnets, you can also make sculptures. When everything sticks to everything else, you can make some pretty fancy designs. This is a rare earth magnet, a very strong one, and a bunch of nuts that I've gotten. And this one here is an electromagnet, but electromagnets are a little different because they need an electric current to work. Check this out. This is sort of a magnet dude with crazy hair. There's an earth magnet here, and this is a giant screw, and these are some metal bits, and then I've got two more magnets at the top here to hold on his crazy wire hair. He's got crazy wire hair because he's crazy magnet dude. Now, of course, we couldn't just talk about magnetic sculptures without maxing it out, so let's max it out. This is a bunch of scrap metal from leftover experiments, and I've got a bunch of rare earth magnets, and now I'm gonna max out a magnet sculpture. Let's see. There you go, a maxed out magnet, me! I made this guy out of metal pipes with earth magnets in between, and these are his arms attached, of course, with magnets. His hand, his little metal pieces attached with magnet. Steel wool for the hair, and of course, hat, non-magnetic. All right, here we go, ready? Want to see a magic trick? Simple copper tube. Drop things through it. Nothing unusual happens, but watch when I drop a magnet through. What? It's not magic, it's science. Because the magnet creates a magnetic field, when it goes through the tube, the magnetic field repels the magnet upwards. Now, the field isn't perfect, so the magnet doesn't come to a stop, but still, it slows down from a fall to a nice, graceful drop. Take a look from above. Pretty amazing, right? Magnets, not magic, science. Today, we're going to be experimenting with the balloon-powered car. Here's how it works. Woohoo!
It all has to do with Newton's third law.
Newton's third law. For every action, there is an equal and opposite reaction.
We don't have to do this now. This is all for later. We can build the cars first, and then we can, let's go over here.
So how do you build a balloon-powered car? Well, I suggest you be science maximites, because there's any number of ways you can build a balloon-powered car. You do not have to follow my design. You should come up with one of your own. It may even be better than the one I built. But I will give you some tips, though, that make it a lot easier. First of all, you need something to stick your balloon on that has an opening on it. I used a turkey baster for this car. I just pop the top off, and remember to tell an adult that you're using the turkey baster. And then you stick the balloon on there, and it allows you to attach something to the car, and it also makes it easier to blow up the balloon. You can use any number of things, even just any kind of tube that you find lying around. It helps you attach the balloon to the car, and it helps you blow up the balloon way easier. The other thing you should think about when you make your balloon-powered car is how you're going to make the wheels roll. Once you've decided on the base of the car, you could use anything, even just a piece of cardboard like this. You can do your wheels in two ways. The first way is to attach the wheels to the axle. This is how I made the axle of this car. I used a shish kebab skewer, and I stuck it inside a straw, just like that. And then I attached the lids to the shish kebab skewer. So the lids and the shish kebab skewer are attached, and they rotate in the straw. That's one way to make the wheels turn. The other way is to tape down the axle or whatever you're going to use and have the wheels spin around on the axle. Two great ways to make your wheels turn, and it really kind of depends on the wheels you're using. You can make your own design and keep refining it and making it better and faster, or do what I like to do and make a whole bunch of different cars. So we've got this one. This one I made out of paper plates, and this is a snorkel. Awesome. This one is the rock car, because there's a rock on it. I've got the dragster model. It's a long broom handle, and it might not work that well, but who knows? And this is my favorite design. It's made out of waffles and an ice cube tray. This is why I make a whole bunch of different cars, because I can race them.
Sunday, Sunday, Sunday at the Science Maxidrome. It's the balloon-powered car winner-take-all drag race of awesome.
First up, the Eliminator. Woohoo!
Better late than never, it's the Procrastinator. Crushing the competition, it's the Terminator. Feel the chill of the refrigerator.
All right!
And last but not least, the Regurgitator.
Well, when you build your balloon-powered cars, you can figure out what worked or what didn't work and try modifying your designs to make them work even better. That is science.
Okay, so here we go.
Amazing.
The friction ramp, it's pretty simple. You just take, I've got blocks of wood with different surfaces.
Amazing.
And then you just slide them down the ramp.
Right. So cool.
Yeah, so what if, to max it out, what if this is us?
We're a block of wood?
No, I mean like we are on the block of wood, and then we can try changing the bottom. I guess a block of wood isn't the right thing to use, though.
Right, yeah. Maybe we could use like a sled.
Oh, yeah, okay, like a snow sled. That's a great idea. Okay, so we'll tell you what. I will portal in a sled for
Are you
us.
sure you want to portal it in?
I'm sure. Just stand back,
Okay.
though. Okay. Ha!
Ah, there we go.
Maxed out friction slide! You ready, Sarah?
Yeah, I'm ready.
Okay, here we go.
All right.
Sarah and I pushed each other around on the sled, which was fun, but it was also tiring.
It's pretty hard. This is
My turn. My turn.
All right.
Oh, yeah! Whoa, friction! Yeah, friction! Yeah! Yeah, friction! But we soon realized it'd be pretty hard to measure how much friction there was. You know how hard you were pushing?
I had no idea how hard I was pushing.
A lot, but that doesn't really help in science terms. So
Exactly.
what do we do?
Well, with your first experiment, you used a ramp. Could we maybe put a ramp up in here?
In here?
In here, yeah.
I guess.
Then we can measure also how far we go so we know how much friction is being used.
Right, so we have our control, and then we have all the, just like the blocks.
Exactly, just like the block.
Okay, great. So we'll get the ramp, we'll get a bunch of wood,
Yes.
we'll get some tools.
Yeah.
Mousetrap. Like I said, we are going to be using mousetraps. Mousetraps as a form of propulsion. That's the force that makes things go, and we are going to be making a boat go. And what is the thing that's going to make this boat go? A mouse. Oh, it's not set. Sorry, I'm really jumpy. Anyway, we're gonna be using a mousetrap. And don't worry, no mice are gonna be harmed in the making of this or any Science Max episode. But mousetraps are really great because they can store energy in the spring. If you see, there's a spring that makes this bar want to snap back. But we can put energy into the spring and store it and then use that energy as it unwinds the spring to propel our boat. But it's a little more complicated than just this, so come on, I'll show you. What we're gonna do is build this. This is the mousetrap boat, and it works like this. I've got the mousetrap, and it's attached to a long arm. That arm has a string on it, and it goes around the paddle wheel, and as the mousetrap unwinds, the paddle wheel spins like that, which pushes the boat forward. Now, it looks kind of complicated, but it's actually quite simple to make, and here's what you need. My mousetrap boat is made with styrofoam, craft sticks, and elastics. You'll also want a pencil, plastic drink caps, a shish kebab skewer, small zip ties, string, and of course your mousetrap. Now, mousetraps can hurt your fingers, so get an adult to help you when you use them. Start with 2 pieces of styrofoam. I like to cut mine into this shape, but the only really important thing is that they're the same size. Your paddle wheel is made from a circle of styrofoam with it penciled through the middle, and it will go across like this. To make the paddle wheel, I use cut pieces of craft stick, or they can be plastic, and make some cuts and then put them in like this, and that is what will make your paddles on the paddle wheel, because that's the wheel and that's the paddle wheel. That's why they call it that. Stick drink caps to the ends of the pencil after sticking it through the styrofoam. I like to use a few craft sticks and elastics to help give the styrofoam strength. Next is the mousetrap, which you want to glue down to a frame of 4 craft sticks. Attach the frame to the boat with elastics, then attach the shish kebab skewer or a pencil to the mousetrap with zip ties. I like to put some craft sticks on the end to make it easier to tie the string to it. Wrap the other end around the paddle wheel pencil, and remember you need enough string so that your stick can lie flat. Okay. Let's try it out. Wind up the paddle wheel. This will be a little hard as the spring will pull back, but that's where you're storing the energy. And when it's wound up, put it in the water and let it go. The paddle wheel turns because the mousetrap is transferring energy that we put in earlier, and it goes all the way. We stored the energy in the tension of the spring. Now that tension is pulling the mousetrap, the stick, and the string, which turns the paddle wheel and makes the boat go. Mousetrap-powered boat! If you want more detailed instructions or other designs, look up Mousetrap Boat. And there you have it, the Mousetrap-powered paddle wheel boat. And this is what we're going to max out today. Come on. Magnetic putty in 60 seconds. This is magnetic putty.
Thank you.
This is magnetic putty.
10 take.
This is magnetic putty.
26.
This is magnetic putty.
2,635.
This is magnetic putty.
I can't count this high.
This is magnetic putty. Magnetic! Oh, it's not a magnet, it's attracted to magnets. Oh, that makes more sense. This is magnetic putty, and this is a magnet. The putty is made of polymers, which means it can flow over itself. It also has lots of iron filings in it, which is why it's attracted to magnets. This is what happens over several minutes. And there you go, magnetic putty. This is water. Things float on water, like pool noodles and wood and toy boats. And now we're gonna do an experiment with how paint floats on water. How's this supposed to work again? Oh! I'm supposed to take the paint out of the can first. This is a fun experiment you can do at home. All you need is a container, some water, and paint. But not just any paint, special paint you use for hydro dipping. That's hydro, meaning water, and dipping, meaning dipping. Carefully pour the paint on the water and add a few different colors. Then take a stick to swirl it up into a pattern. Then you get something you want to paint, and you carefully put it in like so. But don't pull it out as soon as you get it in. You have to spread the paint away because it'll stick when you bring it back out. And then when you pull it out, whoa! Hydro dip. Let that dry, and then you have a very cool painted toy. Let's do some other stuff. This is a bike helmet. If you put tape on what you're painting, you can remove it later to make parts that aren't painted. Skateboard. Whoa! Oh, that's pretty cool. Now to max it out. Hydro dip pants. Wearing the pants when you do this is super messy and not something you should try at home. But the results weren't bad. Science pants! Science pants! Science pants. One of the ways you can experience the power of water is watching it wash away dirt. You can experiment with this yourself by making your own erosion table. To make your own, fill a plastic tub with sand and tilt it up. Cut a hole in the tub at the low end and put a hose with a trickle of water at the high end. Then to complete your model, fill it with a little happy town. This small model shows how rivers cut their course to the ocean by following the lowest point. Try to design your town and the layout of the ground so the river goes around the buildings.
I'll see you later. I'm gonna take a swim in the river now.
There are lots of ways to experiment. Change the amount of water, or the steepness of the angle. Look at the soil, it's all getting eroded over here. Or the way the town is laid out. Every time you do it, the river goes in a different direction. And have fun.
Oh, phew, I'm tired. I'm just gonna lie down.
And that is the power of water. Here is something mind-bending you can do with pulleys. These buckets are attached to the table through a pulley. There's nothing holding this table up except for the weight of the buckets pushing down on the table. So if I took the buckets off the table, the weight of the buckets pulls the table up. But because the buckets are on the table, everything is in balance. Mind-bending, right? Okay, wait, it gets better. If I took a weight and I put it on the table, the weight of the buckets isn't enough to keep the table up. So I have to add more weight to the buckets so the buckets pull the table up. Whoa. And there you have it. It's weird, it's mind-bending, it's science. This is ferrofluid. It is ferromagnetic, which means it's attracted to magnets. And I know what you're thinking. You're thinking, it's not that interesting. Well, watch as I put it next to this magnet. Very interesting. And because it's a liquid, it behaves in very interesting ways. Watch this. Unlike most things ferromagnetic, like paper clips or iron filings, ferrofluid is a liquid, which means it behaves in a unique way. The spikes it creates are following the magnetic field lines of the magnet. You can see the magnetic field in 3D. It's even more impressive when we max it out. This is ferrofluid outside of a glass jar. Now, it's sitting in a pool around this electromagnet. And this is a dial which I can use to change the voltage of the electromagnet, making the magnet stronger. Watch this. Changing the current going to the spiral in the middle turns it into a magnet. The more current I put in, the stronger that magnet becomes, allowing the ferrofluid to climb the spiral to the top. And remember, even though it looks all spiky, it's still a liquid. I will demonstrate with my plastic spoon. And watch this. When I turn the magnet off, it stops being spiky. Turn it on. Turn it off. Science. Magnets. You see, magnets are fun things to experiment with because they are really, they're really interesting. This magnet that I've got here is a neodymium magnet or a rare earth magnet. It's one of the strongest magnets you can get. A magnet is an object that is attracted to anything that is ferromagnetic, which is iron, nickel, or cobalt. And magnets are interesting because they have two sides. There are two poles. I'd show you, but I can't get the chain off. Hold on one second. Ha-ha. There are two. Oh, no. There are two poles to every magnet, just like the Earth. There is a North Pole and a South Pole. That's right, the Earth is a giant magnet. So, if you take kitchen magnets, you'll find that there's two different poles. I've written north and south on these ones. They don't normally come like that. If you put the north and the south together, they stick. But if you put the north and north or south and south together, they repel. They repel. See, they don't want to go together at all. And you can force them together if you want, but if you do, they will spring away the second you let them go. But when magnets repel each other, I find that some of the most interesting stuff. Check this out. This is just a small container, and I've got a magnet in here, and I have a loonie attached to it so that it fits nicely in the container like that. For the top, I've attached two magnets together, and I have another coin on it. And if you put them in there, I've made sure that the two poles repel each other, which means this magnet will just sit there and float. Magnetic levitation. Very interesting. And you can pop the top on that if you want and just carry around a levitating magnet. Now, there's a couple fancier ways you can levitate stuff with magnets. This is just a wooden frame I've made. This is completely not necessary. You can use just about anything in your house. A desk lamp works really well. The important part is I've tied a magnet to the end of this arm here, and this is a bolt, which is attracted to the magnet, but it's got a thread tied to it, so it can't get there. Just far enough that it will actually hang in mid-air. Look at that. It's not attached to anything. It's just being pulled up by the attraction from the magnet. The thing is, as soon as you pull the bolt away far enough, it will lose the attraction and it'll just fall. Very cool. Here's one that's a little bit more complicated, but is also really neat. This one uses disc magnets, which have a circle or a hole in the middle of them here. And you put two around a pencil and then four more in such a position that you can put the pencil against this wood on the side and it will just levitate on its own. You can even give it a spin. Look at that. And if you want to make the levitating pencil yourself, there's step-by-step instructions on how to build an easy-peasy version on our website. Meantime, we are gonna max this out. Magnetic levitation on Science Max Experiments at Large. Whoa. This is a Prince Rupert's drop. It's a piece of glass that has a long snaky tail and a bulb at one end. So what's so interesting about a glass tadpole? Well, I'll show you. And remember, this is just glass. Prince Rupert's drops are very strong, almost as strong as steel. It's all in how they're made. Molten glass is dropped into cold water.
What happens is the outer part of the drop cools off first, leaving the inner part still hot. When the inner part eventually cools, it contracts, pulling everything in tighter and tighter, keeping it under a lot of tension. And because it's round, the force you put on it is distributed all the way around, just like the force is distributed on an arched bridge.
Until you get to the tail. Just the tiniest break in the tail, and
it explodes. All that energy is released in a chain reaction. Why it's so strong you can hammer on one end, but explodes when you break the other, puzzled scientists for centuries.
but now we know it's all in how it's made.
The Wizard Academy. All you have to do is demonstrate true magic, and you will be granted entry.
Send in the next applicant.
Okay, don't let them see you. Don't let them see you. Okay, magic smoke. And here we go. Big entrance.
Behold, it is I, Overwhelmo.
You again.
I only have to demonstrate magic one time, and you have to let me into the Wizard Academy. And last time does not count. So prepare for your mind to be boggled and your eyes to also be boggled, because I shall do a trick. I will just get to it. Here is a book, behold! And now, feast your stupefaction as I produce another book, ha-ha! And then 2 or 3 more times, behold, that's good. Behold! And now, look upon the wonderment as I stack these books on top of each other, like this. And now, feast more stupefaction as I cleverly move the books off the table. And now comes the magic word. Now, I say the magic word. The magic word! And behold, the book is levitating. It is completely off the table. I have done it. Magic!
No.
No?
Not magic, that's science.
But the book is levitating.
No.
Look at it, it's not even touching the table.
No, it's being supported by the books below because of the center of mass.
Preposterous.
I'm afraid it's very posterous. Each book is balanced on the one below in a way that the center of mass is behind the edge of the book below. And the entire stack's center of mass is behind the edge of the table. So it may look like magic, but it's science.
So, I can't get into the Wizard Academy?
No, I'm afraid not.
Good. Alakazam! You will rue the day that Overwhelmo did not. I will return, and then you will see. Oh, ow.
All right, pliers, battery, copper wire. Now, if you've already done the electromagnet experiment, here's another experiment that uses all the same materials, plus these. Ha! Neodymium magnets, some of the strongest magnets you can get. So, here's what you need.
A battery, some neodymium magnets the same diameter as your battery, copper wire, and some pliers.
So here's what you do. First thing is you put the batteries and the magnets together, like that. Then what you want to do is bend the wire so it's touching the top of the battery and goes around the battery and then touches the magnets at the bottom. Here's what that might look like. I say might because you can do any shape you want. I've made a coil here. If you put it over the battery, you'll see it only touches the very top of the battery and the magnets at the bottom. And if I let it go, it spins. It's a homopolar motor. What happens is the battery sends an electric current through the copper wire, and that turns it into an electromagnet, which is attracted to the magnets at the bottom, and it spins. So now let's max it out. Aha! A D-cell battery, which is larger and, of course, larger neodymium magnets. And you do the same thing. Make a coil that only touches the battery at the top and at the magnet, and ha-ha! It spins! Maxed out homopolar motor. But don't worry, this is not the biggest size we're gonna do. Come on. Maxed out homopolar motor. I have 27 D-cell batteries, a giant copper tube, and a neodymium magnet. So I'm just gonna, and then we get rid of that. Put this down. Okay, so the first thing I do is attach the neodymium magnet to the batteries. And I've got all the batteries taped together here so they'll sort of stand up like this. Huh? Giant stack of D-cell batteries. Okay, now what I do is I take the copper coil. I need to get, okay, hold on. I got this. I just need to get the copper coil there. I did it. Okay, so I take the copper and I put it on top of the D-cell batteries like this, and then I let it go. Let it go. Nope, whoa. Homopolar motor. Okay, so that didn't work. But that's okay. I like it when it doesn't work, because that's science. It's not science if it works perfectly every time. I mean, you gotta have some room for improvement. Oh, hello there. Here's a fun science experiment you can do with science and friction together. Take two books, put them on top of each other, and pull them apart. Ooh, not too much friction. But if you take the books and you interleave some of the pages, maybe 3 or 4 parts, and try it again, pull them apart, they're a little harder to pull apart. That's because the friction for more pages touching each other actually starts to add up. So, what if we were to take 2 books with a lot of pages and very carefully and meticulously take each page individually, one at a time, and overlay each one and go back and forth? These are 2 books completely shuffled together. The elastic band is actually just to hold the covers together. All right. So, now the friction between all of these pages, when I try to pull it apart, makes it pretty much impossible. Now, there's 2 things going on here. First of all, when you start to pull the books apart, the pages start to stick together because they squeeze together, because you're pulling and they're squeezing. And the fact that there's so many pages sticking together, the friction builds up to a degree that is actually very impressive. But don't take my word for it, let's max it out. Here is another 2 books, elastic just to hold the covers. This one clamped to the wall, and I'm gonna pull on this one. Science! Still don't believe me? Well, let's max it out some more. 2 books, all the pages layered together, held together only by friction suspended over a giant vat of slime. Now, let's see how much faith I have in science. Friction! Yeah! Okay. Okay, oh no. Okay, now to get down. Okay, hold on. And then. Science! That was close. Moving air is a lot of fun, especially if you use one of these, a Vortex cannon. They're pretty impressive and they use some pretty amazing science. I'll show you how to build one. It's pretty simple. All you need is a plastic cup, you want a balloon, something round, an elastic, scissors or a craft knife, and a pen. Here's what you do. Take your balloon and cut it just where it gets wide. You take the mouth of the cup right there, and you have to stretch the balloon over the top. And then you want to put an elastic around it, keep it in place. And this now is a surface on the top, and that's what you're going to use to pull back and create your burst of air. But of course, the air's not going to go anywhere until you make a hole in the bottom. So here's what you do. You take your round thing and draw a circle, and take your craft knife or a scissors and an adult and get them to help you cut out a hole. And when you pull back on the balloon, a burst of air comes through the hole. But the air has an interesting shape. Now, I know what you're thinking. You're thinking, Phil, air is invisible. You can't tell what shape it is. Well, I can show you. Come on. This is my maxed out Vortex cannon. It's made out of a garbage can. I've got a hole in here, and this is a shower curtain with a ball that I can get a grip on and pull. And then it shoots forward like this. Now, it makes a big puff of air, but again, the air is invisible, so we don't know what shape it is, but I can help with that because I've got this, a fog machine. I fill the inside of the garbage can so we can see what the air is doing when I fire the Vortex cannon. Okay, come on over here. Ready? Whoa! Okay, ready? Check it out.
The Vortex cannon shapes the air into a ring, called a vortex.
It makes a ring. Well, actually sort of a donut.
Because of its shape, the air in a vortex can move much farther than air that doesn't have a shape.
Vortex cannon. Air that has a shape goes a lot further than air that doesn't have a shape. And it's also way more fun. Woohoo! This is a climbing frog. Why does he climb? Because of science. I pull on this rope, and then I pull on that rope, and I pull on that rope, and he climbs up the ropes. And why? Well, because of friction. The secret is 2 straws.
The straws are pointed away from each other at the bottom. This allows it to climb thanks to friction. Take a closer look. When I pull on one string, it pulls straight, which makes the frog pivot. That string slips through the straw because there's not a lot of friction, but there's lots of friction on the other side because of the angle. So one side of the string goes down, which makes the other go up, which means the frog goes up with it, all thanks to friction.
So now, let's max it out. This is a super maxed out climbing frog.
Just like the small version, I have a rope going through 2 tubes. I pull on one rope and the other holds on by friction. Then I switch.
And it does work. It's just a lot harder to pull on the ropes, but it totally works. Whoa, careful, whoa. There, and then this one, and then that one, and then that one. Yeah! A giant climbing frog! All because of friction. Here's another way to defy gravity using friction. Get a plastic water bottle and fill it with rice.
Take 2.
So get a plastic water bottle and fill it with rice using a funnel. Then take a shish kebab skewer and stick it into the bottle and nothing happens. But if you tap the bottle down, the rice starts to pack in a little bit better. See how the level of rice is lower? Which means you can add more rice. Pack it down even more. And you can even use something the same diameter as the mouth of the bottle, like, say, a highlighter. And make sure all the rice is as packed in as you can get it. There. Now the rice is really packed in there. And when I stick the shish kebab skewer in, the friction between the pieces of rice and this wood is enough to lift the bottle using nothing but friction. Now, let's max it out. I filled this 20-liter water cooler jug full of rice, and it's really heavy. I wanted to see if I could lift it using nothing but friction and this dowel, which is just a round piece of wood. All right, here we go. Ah, science! I'd max it out even more, but I don't think I could lift anymore. It's okay, I could just fit.
Newton's first law in 60 seconds.
Newton's first law says an object in motion tends to stay in motion. So why don't they? See, if I was to throw this, It doesn't stay in motion. It doesn't keep going. It slows down and falls to the ground. Well, the whole law states an object in motion tends to stay in motion until an external force acts upon it. So what forces are acting upon this? Well, gravity for one, pulling it down towards the ground, and friction, specifically air friction, slowing this down and making it stop. Now, if you were to have something very light with a lot of surface area, it would really be affected by air friction. You wouldn't be able to throw it very far at all, no matter how hard you tried. So there you go. Newton's first law, an object in motion tends to stay in motion unless it's affected by an external force, such as friction, like air friction. So there you go.
Being a chef is my absolute passion, and cooking up science recipes is my speciality. I'm Buster Beaker, and this is Cooking with Science.
Oh, hello. Welcome to Cooking with Science. I'm Buster Beaker. Delicious. Nothing is more important to have fresh than your seafood. It's what makes the difference between a fresh fish and one that isn't so fresh. If you live by the ocean, you probably know that the water gets high tide and low tide. Look closely, it's the same location. Amazing. But did you know that this is caused by the gravity of the moon and the sun? See, this cookie is the Earth. And this little happy fellow is me. Hello. And this string represents the water around the Earth. If we didn't have gravity to worry about, the water would all be equally deep around the Earth. But here comes the moon, this mushroom. Now, the moon has gravity, and that pulls the oceans towards it a little bit, like this. And that creates high tide there, and low tide here, and a little bump of high tide on the other side of the Earth. And as the Earth rotates and I'm on it, I experience low tide and high tide, and low tide and high tide. Very interesting. But there's another factor. The sun, or this lemon. Now, the sun also affects the tides, but not as much as the moon. Now, the sun does not affect the tides as much as the moon because it's much further away, but it still has an effect. If the sun was here, then the tides would be pulled away a little bit like that, and the tides would be less severe. But if the moon and the sun line up, like over here, you'd get a very, very high tide and very, very low tide. So there you are. That's how the tides are affected by the gravity of the moon and the sun. Delicious. I'm Buster Beaker, and thank you for joining me on Cooking with Science.
Today, we're taking a closer look at chemistry. Ooh. Chemistry is the science of atoms and molecules, the things that make up all matter, and how they interact with each other. Take, for example, this glow stick. Actually, don't take it, because I kind of need it. The glow stick doesn't glow until you... The glow stick doesn't glow until you break the barrier and mix the two chemicals, and they start to glow. Huh? Pretty cool, huh? Chemistry. Now, the chemical reaction we're looking at today is the old vinegar and baking soda volcano. But this reaction doesn't have anything to do with volcanoes. It's chemistry. Now, this experiment is totally safe, but I do recommend you get an adult's permission before you do it because it's very messy. Yeah. First, you're gonna want baking soda and vinegar. These are your two main ingredients, but you'll also want dish soap and red food coloring if you want it to look a little bit more like lava. Now, I like to mix the baking soda, red food coloring, and dish soap together with a little warm water, so all you have to do is add the vinegar. And when you do, this is what happens. And there you go, chemical reaction. Now, I know what you're thinking. You're thinking, Phil, how much vinegar or baking soda do I use? Well, I'm not gonna tell you. This is where you can be science maximites. Try different amounts. More vinegar, more baking soda, more dish soap. Who knows? Write down the amounts each time you use it and find out what amounts work best. That's called science. Plastic is great, and plastic is everywhere. But the problem with plastic is it isn't very biodegradable. It doesn't break down in the environment. I'm still on hold. Oh, well, there you go. Back for another couple years, I guess. But here's a way that you can make bioplastic. It's fully biodegradable because it's made of natural materials.
The recipe is easy. 2 parts cornstarch, 3 parts water, a few drops of cooking oil, and some food coloring to make it whatever color you want.
Purple, science purple.
Mix it up and it turns into a paste.
Now what you'll need are 2 things. 1, an adult, and 2, a microwave.
Put it in for 30 seconds.
Clock wipe. There we go.
Then take it out and mix it some more until it cools down. Then you can pull it out and use your hands to sculpt it into a shape or take the shape of something else.
Once you put it all the way around, you can turn it into a little flower pot.
Once you've sculpted it,
you need to wait for it to dry, which will take about a day. Clock wipe.
After waiting a day...
What? It's been a day? Oh.
You have something made out of bioplastic. Like this little flower pot you can use to grow a small plant.
And then when it grows big enough, you can take this biodegradable flower pot and plant it right outside in the dirt, and this pot will biodegrade and turn back into dirt. Pretty cool, right? Well, let's max it out. Biodegradable frisbee! Check it out! It's a frisbee, but it's biodegradable. So you throw it around in the park, but if you lose it, it turns back into dirt. Ha-ha! What, not enough? Okay, clock wipe! Biodegradable lawn chair! Use it for 1 season and then return it to the earth afterwards. I think this is one of my best Science Max. Okay, bioplastic lawn chair, not as strong as regular lawn chair. We've learned that lesson now, so that's good to know. I mean, how would I have known if I hadn't tried it? Okay, I'm here. Wow.
That's perfect. 1 particle impulse controller for you.
All right, thanks very much.
No problem.
Appreciate it.
Enjoy.
Thank you. Well, my very own particle impulse controller, okay. That's as heavy as I thought it was gonna be. All right, Science Maximites, this episode of Science Max Experiments at Large is gonna be a little different because today I'm not gonna have an expert come and help me because I'm gonna move that giant, heavy particle impulse controller all the way across the parking lot and all the way up that loading ramp by myself with nobody's help. How am I gonna move a giant, heavy machine all that way if I can barely even budget? Well, I'm gonna give myself superpowers, super strength with the power of simple machines. And the first machine we're gonna start with is the lever, which I guess I should go back to the lab to tell you about.
All right, Sal, I'll see you next time. Oh, hey, how you doing? Let me guess. You got some work to do and you need it done easy, right? I mean, look at this book. I mean, you could pick it up, but what, are you gonna be some sort of book picker-upper person now? Is that all you're gonna do? Is that gonna be your life, just picking up books left, right, and center? No, you're smarter than that. You know what you need? A lever. Like this. Now, I know what you're thinking. I know. You're thinking, hey, this is just a plank. You're right. That's because you're smart. A plank can be a lever. All you need is 2 sides and a place for it to pivot. A fulcrum. It can be anything. Look at this. Bam! Now it's pivoting. I put the book on this side, and then I push down on that side. I'm doing work easy. Hey, look at me doing this work over here. If I want to do more work, I could move the fulcrum a little bit further over. Now I do lots of work, but I lift the book a lot further. Look at that. Whoa! Wow! Whoa! Yeah! Huh? What do you say? What do you say? Huh? Huh? You don't like this lever? Don't worry. Hold on. I got another one for you here. Hey, take this stick. All you need is 2 ends and a place for it to pivot. Like this. Bam! Now, it's a lever. This side goes down, that side goes up. Down, up. It's a lever. It's a lever. You want to make a catapult? Use a spoon. The place where the spoon pivots is the fulcrum. And now,
It's a lever. It's a lever. It's a lever.
Look at this lamp.
Now, it's a lever. Scissors, 2 levers. Your forearm, it's a lever, 2 ends, and the fulcrum where it pivots, yeah, the fulcrum can be at one end. Crazy. This fish, you guessed it, now it's a lever. And now you know your levers. Did you know it's easier to float in salt water, like in the ocean, than it is in fresh water, like a lake or a pool? That's because not all liquids are created equal. They have different densities. This is fresh water, or it doesn't have anything in it. And this is sugar. If I was to put 1 scoop of sugar in this water and stir it around until it dissolves, now this liquid is more dense than before I put the sugar in. Here's an experiment you can do at home using liquid density. This glass just has regular water with yellow food coloring in it. This glass, green food coloring and ½ a cup of sugar in it. This one has a full cup of sugar in it, and this one has 2 cups of sugar in it. Now, when you do this at home, you'll definitely want an adult to help you because you have to heat the water if you want to dissolve that much sugar in 1 glass of water. I'm gonna put them all in 1 container. You can do this at home, and when you do, I suggest you use a very small container because you have to be very careful when you put the layers in. You can use a turkey baster or a straw. When you put your finger on top, the air pressure will hold the liquid in and you can just drop it in. But these kind of take some time, so I'm going to use the syringe of science. I'm gonna use the most dense liquid first because that's the one that's gonna want to be on the bottom. I carefully put it on the bottom of the container. The next layer, be very careful, and you'll see that the red and the blue aren't mixing because they have different densities. The blue is heavier than the red. We'll add the green, and you can see even when it drips into the red, it comes back up to the top because the green liquid isn't as dense as the red liquid, and the denser liquids push the lighter liquid up. And now we're gonna add the yellow, which of course has no sugar in it at all. And there you go. All the layers stay separate. If you put it on a light, you can really see it. Liquid densities. Now, let's max it out. Ta-da! The longest length of liquid layers. 12 liquids, all organized by density. Starting from the bottom, we have honey, corn syrup, chocolate syrup, maple syrup, dish soap, whole milk, water, dyed blue, vegetable oil, extra virgin olive oil, rubbing alcohol, baby oil, and lamp oil. Liquid density. I really, really want to mix it up, but it took me a long time to make this, so I'm not going to. Okay, Science Maximites, prepare to hurtle through the cosmos. I am Captain Phil, and today we're going to be building rockets on Science Max. Now, we've built rockets before, like this one, powered by air pressure. And this one, stomp rockets, which were also technically powered by air pressure. Air pressure rocket! But today, Science Maximites, we are going to be building rockets powered by chemistry! Chemical-powered rockets! Away! Okay, I promise it'll be more exciting than that. Because today, Science Maximites, we are going to be looking at chemistry. Chemistry is when 2 molecules combine to make another molecule. Like magic, ooh. So let's take a look at what will be powering our chemical rocket. This, it's an antacid tablet. When you put an antacid tablet in water, it makes little bubbles of carbon dioxide gas. This happens because of a reaction between 2 kinds of molecules called acids and bases. Like vinegar and baking soda, but all contained in a small package that won't start working until you put it in water. If we contain the reaction, the carbon dioxide gas builds up and creates pressure. High five for science. All right, so let's look at our chemical-powered rocket. What you need is one of these. This is a This is a film canister. And ask your parents what that actually means because they're not used for holding film anymore. You can get these at craft stores though to hold paint or little things. But really all you need is a plastic container with a good lid that snaps on nice and tight and keeps the air in. And then of course what you need are your antacid tablets and a little bit of water. So pour in some water and then put in your antacid tablet and snap the lid on. Flip it over and wait for the carbon dioxide gas to build up, which will build up pressure, which will launch your rocket. Ha-ha! So there you go, a chemical-powered rocket. We're gonna use uncooked pasta, which is less delicious, but it's great for building. We're gonna make a pasta bridge. Here's how you do it. First, you wanna start with a plan. And then you want to take your pasta, I'm saying pasta, but of course spaghetti is usually the best thing to use, and lay it out on your plan. The reason you have a plan is so that you can make sure all of the spaghetti is exactly the right length. Lay it out on your plan, perfectly aligned like that, there. And now it's time to glue it all together. Now you can use white glue, but it takes a long time. So I suggest a hot glue gun, but make sure you get an adult's permission before you use one of these, okay? So you take your plan, you lay it out, you glue it up. Don't glue it on the paper because that will be bad. And you will end up with your truss, and it looks just like this. Now remember, you want 2 sides because those are the sides of your bridge. And as you can see, I've used several strands of pasta because that'll make it a little bit stronger. Once you have your trusses, it's time for the next part of the plan. This is the roadway, and it works the same way. Lay out your pasta, glue it up, and bam, there it is. Now, you put your trusses on your roadway, and you glue them all together, and you also want to put some struts along the top here, probably, to keep it nice and rigid. In the end, you will end up with a fantastic-looking pasta bridge. Pretty good, huh? Pasta bridge. No other bridge could claim to be 100% pasta. Minus the glue. 99.8% pasta. 0.2% glue.
I say there, Captain. Set sail. Set sail for the land of pasta bridges.
Now, if that was pretty fast for you, don't worry. All the instructions are gonna be on our website. Now, a bridge isn't a bridge unless it spans a gap, because that's what bridges are for. So you put your pasta bridge up there across the books like that, and then you can see just how much weight the bridge holds. It's pretty impressive. If you build it right, even something as flimsy and as delicate as pasta can hold quite a bit of weight. I like to use big, heavy blocks and put them in the middle where there is no support from the books whatsoever, and just keep adding heavy things and see how much weight the bridge will hold before it breaks. How much will it hold? Well, I'm not gonna tell you. That's where you get to be Science Maximites and find out for yourselves.
Phil to Mission Control. Come in, Mission Control. This is Mission Control, Phil. We read you loud and clear. I would... Oh. Greetings, Science! Greetings, Science Maximites! Welcome to Science Max Experiments at Large. My name is Phil McCordick, and today we're gonna be building an air-powered rocket. Too difficult, you say? Nonsense, it's easy. It's not like it's rocket science. Hey, it is rocket science. Cool! Here's what you need. You need a bottle and a cork. Make sure that the cork fits nicely into the bottle, and then you need an air pump, because you can't have an air-powered rocket without air. And on this air pump, you need a pin, the special kind that you use to inflate basketballs or volleyballs or stuff like that. Now, what you want to do is push the pin through the cork. You might want an adult's help for this. Push it through until it goes through on the other side, and then make sure you get a good seal with the bottle. Now you're ready to launch your rocket with air pressure. But first, let's do a few other things. Take your cork and put it in a tripod launcher. You can make this out of pencils or anything you want, as long as it stands up nice and solidly. And then, of course, you want to decorate your bottle so it looks like a rocket. This is my rocket. Pretty good, right? So stick the bottle on the cork like before, like that. And then you stick the pin in the bottom. And what we're gonna do is we're gonna inflate the bottle with air pressure, and then it's gonna launch. Okay, here we go. You know, rocketry really isn't something you should do indoors. Come on.
Hey, this was supposed to be a field. What's going? Why are there? Oh, it's in my shoe.
Oh, this will do nicely. Now, don't forget to do this with an adult, and don't forget your safety glasses. Now set up the rocket in a nice big open area and make sure it's pointed away from you. And then what you do is you pump the air pump. And it puts air into the rocket, which pushes down on the water, which will push down on the cork, until eventually So be Science Maximites and come up with your own rocket design. Try different amounts of water, different fins, even a different size bottle. Try it for yourself and see if you can get one that goes higher than mine just did. How did I get in? I think it was this way. I'm here at the Ontario Science Center, and this is Anthony. Hey, Anthony.
Hey, how's it going?
Good. So you are amazing at bubbles.
I am. I've been practicing for a while. Let's get started.
Okay.
You're gonna make an okie dokie sign like this.
Uh-huh.
You're gonna dip it right into our bubble solution. Come on, get right in
Okay,
there, right in there. Make sure you get it all. Oh, that's a little too much.
Well,
That's
then I
good.
can make two.
And then you're gonna keep that okie dokie sign. You're gonna blow very gently.
Nice.
I brought these two giant sticks here, and I don't know if you noticed, but I've got a smoke machine here.
Right.
So we'll turn that on, and then if you press that green button there, you're gonna shoot some smoke, and we're gonna try to catch that smoke in a giant bubble. You ready? Okay, and I'm gonna try to... Oh, that was so close.
great.
Did you see that one? You give it a shot. Nice! Oh, check that out! That was amazing! That was huge. Try it again. Let's see if I can get the smoke machine. Here we go. Go for it, go for it. Push right towards. Oh, check that out! You did it! Look at that! Look at that! No! Smoke, and it bounces on the floor because the floor, it doesn't have any oils like our hands do. Isn't that amazing?
That was
oh my
great.
God, that was so cool.
That was great. You know what I think we should do?
What's that?
Giant bubble, tons of smoke.
Done.
Okay, here we go.
Let's do it. You ready?
Giant bubble, tons of smoke. Go.
Awesome! Oh my God! Look at that! Amazing! Look at that! That's crazy!
Maxed out bubble. Well, there you go. Giant smoke-filled bubbles.
Awesome!
Yeah.
Judy and I tried mixing the cornstarch mud using a drill with a mixer attachment, but it didn't work. We should have known better. Here's the mixer in our cornstarch mud. Usually, a mixer works by going really fast and mixing everything together. But remember that cornstarch mud is a shear thickening fluid. So, when the blades of the mixer tried to go fast through the cornstarch mud, it did what it always does, turn solid. The faster and harder you try to move it, the more solid it will become. This means the only way to mix it would be if we made the drill go very, very slow, which wouldn't speed things up at all. So with the drill another lost cause, Judy and I need the biggest thing around that could mix stuff up.
Come on back. Good. Little bit more. Perfect. A cement truck is the perfect thing to mix because all we have to do is get all the cornstarch up in here and it'll mix it, and it doesn't move it too fast. It goes nice and slow, so hopefully a shear thickening fluid will be fine. I'm gonna get Judy. She's driving the truck. Hey, Judy, that's perfect.
The only problem is we needed to get all of those bags of cornstarch into the hopper of the cement truck.
I didn't think it'd be this messy.
We needed to call the entire Science Max build team to help us out.
This This is possibly the messiest thing I've ever done. Awesome! Woo. Hey, Judy, you wanna lift up any bags?
I'm okay, thanks.
That's okay. I'm having a lot of fun, so I can do them.
Cool.
Oh no! Oh no! Oh no! Yeah! I got most of it. I got most of it. All right, I think we're done. I think that's enough bags. Let's start the mixing! So, what do you think, Judy? Do you think it's gonna work?
I think so, because you're mixing at a very large volume, but at a very low speed.
Yep.
So throughout the process, it'll stay a liquid until we're ready to run across it.
That sounds exactly like the kind of science I like to see. You know what I really like is that every time I move, more cornstarch comes off. It's like I'm a human fog machine.
Here's another fun way you can play with elastic force. Take a milk carton. I prefer Science Max milk because it's the creamiest. 2% cream, 100% science. Wrap some elastic bands around it with some popsicle sticks on the bottom, sort of like feet. Then take some clamshell packaging, which wraps just about anything you buy nowadays, and cut out a square or a rectangle. Then wrap some tape around that square with an elastic in it, and put the elastic on the feet of your milk carton. Then wind it around and make sure you go backwards so your paddle wheel boat will go forwards when you put it in the water. And there you go, a paddle wheel boat. Now it is time to max it out. Ahoy, the SS maxed out elastic force paddle wheel boat mattress. I need a better name. But I've made a giant paddle wheel boat that will work on elastic force because I've got surgical tubing as my elastics, and that's an air mattress. And then I use some lumber to hold it all together. And of course I need a paddle wheel, and what better thing to use in a pool than a flutterboard. Okay, here we go. So normally you're not allowed to wear your clothes and your shoes in the pool, but I got special permission because of science. Besides, I'm not worried at all, so I didn't wear my swimming outfit because I figure I can totally do this entire experiment without even getting wet. That is how confident I am. All right, now the tricky part, we'll be getting onto the mattress. Okay, here we go. Ha-ha! Whoa. Ha-ha! The SS Science! Hey, SS Science, that's a great name for this. Look, it works great, and I managed to stay totally dry. Huh? Well, almost. Whoa, oh, oh. Haha, you thought I was gonna fall in the pool, but I didn't. Uh-oh. My flutterboard has stopped moving, and I'm in the middle of the pool. Almost. Yeah. Didn't think this through. No. 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 No, that's not going to work. Maybe I'll wait. So you know that some things float and some things sink, like rocks, or wood, or full water bottles and empty water bottles, or carrots, foam, waffles, screwdriver, playing cards, plasticine, tinfoil, potato, my watch.
Wait. That wasn't supposed to go in there. So how do you make a boat? You make it out of something that floats, right? Well, most boats are actually made out of metal. Tinfoil is metal and, well, it sinks. But if you fold tinfoil into a boat shape, it floats. And boats don't only float themselves, but they can hold people and cargo. In fact, there's container ships crossing the ocean at this very moment that are holding thousands of tons of cargo, and they're all made of metal, which doesn't float, it sinks. So how do boats do it? Are they magic? No, of course not. Boats are science. And here, you can be science maximites. Get some tinfoil and cut it into the same size pieces and fold a couple different shapes of boats and see which one can hold the most weight before sinking. And now it's time to max it out.
But before we do, here's how you can fold your own tinfoil boat in less than 15 seconds. First, take a square piece of tinfoil, then fold it in half. Fold one corner down and the other corner down. Then open it up and ta-da, you're done. If you want instructions on how to fold a more complicated boat, go to our website. The plan is to take our small hover disc and make one big enough to ride. So I'm off with Helena to another part of the Science Center to meet Russell, who has some ideas on how we can do it.
Oh, hey, Russell.
Hey, hi, Helena. Hey, Phil.
How you doing, Russell?
How you doing, Phil?
So this is the hover disc.
This is our small hover disc, yes.
How does it work?
Well, obviously you sit on here,
right.
Air will go into here. It gets vented through all these separate holes here, so we get an airflow over the entire area. Hopefully this will work to pick someone up. All we need is...
Air.
Oh, well, that's easy, because the small one worked like this, so we just put the balloon on, right?
I hope you got the
Okay, so we put the balloon on the... hold on. Larger balloon!
Oh, okay.
Sorry.
That's okay.
Okay. Yeah. Uh-oh, twist it so it doesn't...
He's losing his air.
Okay.
All right. On you get. You grab
Right.
one side, I'll grab the other.
Okay, here we go.
Go.
It doesn't
feel way too much.
It doesn't
friction
feel
on
like
it.
it still feels pretty frictiony. I think we might need something more than a balloon. So what do we do?
Well, I think we need more consistent air going through here.
Okay. So not a balloon.
Not a balloon. Something, I don't know, opposite to a vacuum cleaner?
Opposite to a vacuum cleaner. That would be
Like a leaf blower.
Like a leaf blower.
a leaf blower.
Right?
High five.
Yeah.
Awesome idea.
Yeah, leaf
so
blower it is.
why don't we make a couple larger discs and we'll hook some leaf blowers to them and we'll see what happens.
Definitely give it a go.
Okay, great. That's right. Paper airplanes. Ha ha. Look out. Woohoo! Believe it or not, you can learn all kinds of science from paper airplanes. So let's build some. We are going to do a paper airplane which actually holds the Guinness World Record for the longest paper airplane flight. Pretty cool, huh? First, you fold the paper in half like this, but then you open it back up again, and then you fold in the corners like this. Now, don't worry if this is really, really fast, because you have all the instructions on our website. Then you can fold the paper down like this, make sure it's about 2 centimeters from the bottom, where the point is there, and then you fold the corners in just like you did before. But these ones are just guide folds. We use guide folds to help us fold other folds, basically. Now, we fold again using the guide fold lines you just made. And I like to call this fold the shirt collar fold, because it sort of looks like a shirt collar when you fold it. Now, we fold again on the fold that you made before. Folds in like that and in like that. And now we fold the point down to touch the edges right like that. And this is a guide fold, so do it very strong. Unfold it. Now you fold it in half like this. And see that guide fold line that we made there? What you're gonna do is you're gonna take the tip and you're gonna fold it in to touch the guide fold line like that. And this is also a guide, and open it up. And here's the trickiest part. See how it's bent like that? You push it open like this, and this is called a pocket fold because you wanna make a little pocket and push it up against there. Fold it flat like this. Fold this tip down over there like that. Then fold it around the back side. Then fold the wings down like this and like this. And here's the extra special bit. We're gonna use some stabilizers on this plane. Fold up the stabilizers on the ends of the wings, and ta-da, the Sky King paper airplane fold. Now, as science maximites, you know that there's lots of ways you can learn how to fold paper airplanes. Get an adult and look up paper airplane designs on the internet, or take a book out of the library on how to fold paper airplanes. All right, Talina, you ready?
Yep.
You're gonna pour all your baking soda in the fish tank, and I'm gonna pour the vinegar into this bucket, because you don't wanna pour them together right away. Okay, you ready?
Yep.
Okay, go for it. When you're doing your PhD in chemistry, do you get to do stuff like this?
Yeah.
Really?
Got to do a lot of fun reactions in the lab.
Oh, I'm jealous. Have you ever done this much vinegar and baking soda in one time?
I can't say I ever have.
There you go. That's what I like to hear. I already put the soap in the bucket so it would mix with the vinegar when I poured it in. Are you done your baking soda already?
I am.
I'll pour faster. Oh, faster.
It smells vinegary.
It smells vinegar. It makes me want French fries. Okay, Talina, you take this very full bucket of vinegar and dish soap.
Thank you.
I will take this one. Uh-oh, we still have our third bucket. Okay, I'll do these both at the same time. Okay, ready? On the count of 3. 1, 2, 3. Whoa! 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 Wow.
Okay.
That's awesome. So the one thing it didn't do, it didn't shoot up in the air though.
Yeah, it's because the top is quite open, so you would need to constrict it to get it to shoot up.
Oh, yeah, because we're using just sort of a square, a rectangular prism container. We should get something that's maybe something more like our vinegar bottle, right? Because there's lots of space down here, but then it forces it into a tighter opening at the top there, like a volcano.
Yep.
And what else can we do to make it even more powerful, to max it out?
Vinegar is only 5% acid, the rest is water, so you could try using 100%.
So what kind of acid is vinegar?
It's acetic acid.
So vinegar is actually only 5% acetic acid and 95% water. So you can get 100% acetic acid?
Yeah.
Can you get 100% acetic acid?
Yes.
Awesome. Why don't we get a container that's sort of shaped like a funnel, like a volcano, and 100% acetic acid, and we'll do it again.
Sounds good.
All right, let's do it. Today we're combining 2 different chemicals to create a reaction. Sometimes chemicals can combine in a way that makes them very different from how they started out. For example, this is sodium, or Na on the periodic table. Now, the sodium tablets are in mineral oil because sodium reacts very strongly with water, even the water in the air, or especially the water in my skin. Watch what happens when I drop a sodium tablet into this beaker of water. Very cool and very dangerous.
And this is chlorine, or Cl on the periodic table. Chlorine gas is very poisonous.
So, so what happens if we combine these 2 deadly substances? Do we create some sort of super poison? Something more deadly than anything else known to science that causes fear and chaos in chemistry labs all over the land? No, we create salt. Good old normal table salt. These 2 substances combine to make NaCl, salt. Something completely and totally safe. Chemistry. Oh.
Foam. 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 How can they all be foam? Well, foam usually means something to do with bubbles. There's all kinds of solid foams out there, and they can be squishy or not squishy. And they're usually light. Air is an insulator. That means it does not conduct heat or cold very well. You see, I cannot tell this ice is cold until I get my finger really close to it. Yeah, there it is. There, I feel it. And because foam is full of air bubbles, it makes a great insulator. That's why we make coolers out of foam. So what's the best, most advanced foam out there? It's this. It's called Aerogel, and it's 98.2% air. It is super light because it's mostly air, and it's a great insulator because it's mostly air. It's great to pack things in as well, and NASA uses it on the Mars rover and in spacesuits because it's such a good insulator. Cool. Or not cool, because, you know, it's an insulator, so it would protect from the cool. I'm an acid, and I'm a base, and we are enemies. Whoa, well, we're not really enemies. Yeah, that's true. It's all about how we react chemically. You see, as an acid, I really want to give protons away. Protons? Who needs your protons? Get your protons here. Protons, I got more than I want. I don't need them anymore. And bases, we need protons. We'll do anything to get them. Protons, you can protons away. I'll take some protons. You think that when you get these two together, you'd have some pretty great chemistry. But the truth is, when they're together, they often don't react. Whoa. That is, until water gets involved. Once you have water, acids and bases react. Whoa. Here, take some protons. All your bases belong to us. Here you go. Take some protons. I don't need more. I want more. I want more protons. Here. Water is a solvent, allowing the chemical reactions to take place. Depending on the strength of the acids and bases, that reaction can be mild. Would you like a proton? Oh, no, really, I could. Please take it. Oh, well, thank you, that's very generous. Have another. No, perhaps, maybe I will. Here's one. Okay, maybe just one. But if the acids and bases are strong, the chemical reaction can be really extreme. This is what's going on in the antacid tablet, and why, without water, nothing happens. Oh, water! Water! Come on! What'd you do? All right, let's build our catapult. The first step, take 4 pencils and stick your popsicle stick in between so you have 2 on the top and 2 on the bottom. And then use your elastic to go around and around and around. That's why I like building things with elastics, because it makes it very fast to tie things together, because once you go around and you have it nice and tight, you just pop it over the end and voila, it stays together. And that is how you start making your frame. Put more pencils on that side.
And another popsicle stick on the other end, held on at the corners with more elastics. Then, take even more elastics and put them right around the middle until you get
this. I've added a few more elastics around the middle here, and that is where we're gonna get all of our elastic force. I think I have 6. The more you use, the better it's going to work. Take your popsicle stick, stick in between the elastics, and then start spinning it around. Here's the reason I use pencils and popsicle sticks, is because the pencils are a little bit longer, which allows you to twist the popsicle stick around in the middle and build up the elastic force. Now, because I'm twisting, the elastic force we're using here is called torsion, or twisting force. When you feel you have enough torsion, pull your popsicle stick down a little bit so it won't unwind on you, and you'll see that you have all kinds of elastic energy. Then take your spoon and stick it on the popsicle stick, and you can also break off the popsicle stick if you want to make sure it's the right length. And it works like that. To make the frame, you just need more pencils and elastics. The trick is to make a triangle with 2 pencils attached to your frame. They should stick up right where your catapult arm would be fully upright. Then, take a final pencil and put it across the top. Don't forget to pull the arm back before you put the pencil across, otherwise it'll end up on the wrong side. Now, this is very complicated and I went pretty fast, so if you want the step-by-step instructions on exactly how to build this, go to our website. And there you go, a catapult of your very own that you can use to knock down very small castle walls. I've also built a larger catapult using all of the same principles. Pretty good, huh? It's got a longer arm, which means I can throw marshmallows even further. Whoa. Or I can throw larger marshmallows, or I can throw very large marshmallows. Whoa. Now I know what you're thinking. You're thinking, Phil, is that the largest catapult you're gonna make? Well, of course not. This is Science Max, experiments at large. This is a balloon, and this is an orange. When you put them together, a chemical reaction happens. How'd you go in there for a minute, didn't I? No? No? All right. Well, you can actually do a chemical reaction between a balloon and an orange. You see, balloons are made of latex, which is a kind of polymer that's very, very stretchy. And orange peels contain a chemical called limonene. Limonene breaks down latex. So, we have 3 questions. The first is, why does this happen? Well, like I said, it's all chemistry. You see, balloons are made of polymers, chains of molecules held together by chemical bonds. A limonene molecule attacks those bonds. Nom nom nom, nom nom nom, nom nom nom, delicious. And breaks it, that separates the polymers, and that pops the balloon. But remember, it only works with natural latex. So make sure you're using natural latex balloons. Second question, why do they call it limonene when it's in orange peels? I mean, yes, it's in lime peels and lemon peels, but the chemical itself smells like oranges. They should call it orangenine or citrus fruitinide or... Anyway, third question, should we max it out? Of course we should, come on. 200 balloons versus 2 bottles of limonene. Ready? Go!